So far in the course, what we've been talking about has been limited to one sample largely, and just more recently our topics have gotten into two samples, and it made a difference whether our samples were independent or dependent. And that idea about independent samples and dependent samples, that didn't have anything to do with the measurements we took. I mean, the numbers were the numbers, but it influenced them. So how we conduct an experiment can influence how we analyze it. And so what we have to know about how an experiment was done, all that comes under this big general heading of experimental design. So we'll just talk about a brief introduction to some experimental design concepts today. If you continue on in the 5023 course, the Statistics for Experimenters 2, and then later experimental design, you get into more and more of these topics. All right, so it's how did you do the experiment? Because that how you did things then influences what our analysis is going to be. Okay, so some basic terminology within experimental design. We have two types of studies that we typically see in statistics: observational studies and designed experiments. So an observational study is just then the data or the responses that naturally occur, and we observe that information and we record it. Weather data, stock market data, right? Those are examples of observational data. Designed experiments, then that's where we have a plan, all right? A planned procedure or a condition that we impose, and how do we do this, okay? How do we construct our samples? Are they independent or dependent samples? Because that's important, all right? So that's what we mean by a designed experiment. Within a designed experiment, we can talk about a treatment. Generically, most statistical references refer to this imposed condition as a treatment. And so here, written as experimental condition under investigation. Some textbooks will call this a factor. A factor can also have a broader definition, but here it's just the conditions that we're imposing, okay, within our designed experiment. All right, the experimental unit is the receiver of that treatment application. All right, so our treatment, we may have a treatment may be a medicine, and we have a placebo and an active medication that we're giving to subjects. All right, so we give it to an individual subject. We may measure the subject several times, but the patient is the object to which the experimental condition is applied. Subsampling in an observational unit may be the same as the experimental unit, or it could be some finer measure on that experimental unit. And we'll look at a few illustrations of this then next. So probably most common we can relate to, since we're all sitting in a classroom here. All right, students in a statistics class. All right, they are taught by either of two methods. So I have two classes of size 30. Two classes of size 30 are assigned to method 1, and another two classes of size 30 are assigned to method 2. So here, when we define our treatment, the shorthand here by me and for almost everywhere in statistics, TRT is a shorthand for treatment. All right, the treatment we look at here is method, and method has two levels. All we know is that they're 1 and 2. They could be totally computer-based. One of them could be face-to-face. So we don't know what the details of the methods are. Okay, the experimental unit, EXP, is my shorthand for experiment or experimental. So we have experimental unit. To what is the treatment applied? Okay, the experimental unit is the class of 30 students. All right, method 1 is applied twice, once to the first class, once to the second class. Okay, the methods are not applied 30 times, right, or well, I guess 60 times if there's 60 students in both. The methods are only applied twice, once to each classroom. Okay, so what received the method was the class. Now what we measure then may be student performance. That would be the observational unit or the subsampling unit. So to shorthand that subsampling unit, then would be the student. All right, how did you do this? How did you apply the methods to an individual student or to a class of students, right? That's a design issue. Let me look at a couple of other illustrations or examples. In the area of, let's say, forestry. In forestry, they may be looking at a treatment. They may have a pesticide with a specified number of levels. Okay, this pesticide is applied to the experimental unit. Maybe the experimental unit is a stand of trees. So a stand is a group in close proximity to each other, applied to a stand of trees. The observational unit or subsampling unit, so OBS can be observational unit. The observational unit would be an individual tree. On the individual tree, we may measure some degree of infestation of this pest that we wish to control, or other health characteristics of the tree. All right, within animal science, suppose that our treatment is a feed ration. All right, to these animals, a particular diet or feed ration is administered. The experimental unit, the animals are housed together in a pen or grouped together in a pen. So the experimental unit then is the individual animals are not fed, but say a pen of animals. There's competition for food. All right, the behavior within the pen influences feed intake. All right, our subsampling or observational unit, we're going to measure the health characteristics and weight gain and other such things on an individual animal. Okay, so here the animal scientist would know that the animals being penned together, and with regard to these feed rations, how many animals are penned together and such is going to influence the outcome, the different response variables. Now, if the treatment were, say, an inoculation method, the inoculation is applied to an individual animal. Okay, they're vaccinated or with respect to a disease, or given some other medication in the form some sort of an injection. All right, they may be housed together as a pen, but what the inoculation is doing isn't influenced by how they're treated. So I can regard each of the animals there as the experimental unit. Possibly depends on what we're studying. So the animal scientist can answer that question for us. So just because they're penned together doesn't always necessarily mean that the pen is the experimental unit. And so if that seems foreign to you, you're probably not in animal science. All right. So likewise, if you're not into forestry, that didn't make as much sense there. Okay. Got one more. And this was a toxicology study. In an environmental toxicology study, in this particular case, we have a treatment. Had to deal with the toxin level. And the experimental unit. The exposure to the toxin was controlled because it was applied to an aquarium. All right. The subsampling units or the observational units in there were the individual fish in the aquarium. All right. So experimental unit, how many experimental units you have control, that's really your sample size. All right. Putting more fish in the aquarium doesn't make me, that doesn't mean that experimental condition of toxin level has been imposed more than once. They're all together, all the fish are experiencing whatever level of toxicity that is controlled in that environment. All right, so we could keep going with lots of other things, but hopefully these are just a few illustrations to see it makes a difference what object receives the application of the treatment. Okay? It also makes a difference whether those objects are in the samples that are independent or dependent samples. Okay? There is always variability in the data we collect. Do you agree with that statement? You take measurements on if it's an observational experiment, the weather's not the same every day, there's variability there, the stock market changes, there's variability there. If you look at a designed experiment, not every subject or experimental unit is going to respond in the same way to an imposed treatment level. Okay? Experimental error is the measure of variation among experimental units treated alike. And so the idea here is that let's say I have 3 treatments, treatment 1, 2, and 3. All right, I have subjects within each of these treatments. Don't have to be the same number. Okay, and so when we talk about treated alike, all right, we're looking at variability this way. All right, those are treated alike. How variable are these observations? Treated alike. How variable are these? And likewise in this list. Okay, variability among things treated alike. There's also variation among experimental units assigned to different levels of a treatment. That is, so here among different levels, there's variability this way. That's what we mean by among the different levels of the treatment. Variability from here to here to here. 2 sources of variation, treated alike and among those treated differently. Replication. When a treatment level appears more than once in an experiment, it is said to be replicated. So you've imposed a condition on more than one experimental unit. Then you've replicated. So it's a little bit of a grammatical thing. We talk about something being a single replication. Replication, the very definition of replication means more than once. In a statistics literature, we tend to stretch that definition a little bit. Okay, so we can talk about things in a single rep. That just means in a single application of the treatment level. Okay, more replication allows us to measure experimental error. So these are the experimental units here. So the more I have, if I have replication here, I'm able to measure experimental error, variation among things treated alike. If I'd only done each of these treatment levels once, I would have no experimental error. Agreed? Okay, so more replication allows us to measure experimental error. It also allows us to improve precision or a margin of error. And what does that mean? Well, think about what we did when we talked about our variance associated with an individual sample mean. That was equal to this population variance divided by the sample size. So that sample size is replication. So if replication increases, what happens to the standard error of the mean? The variance of the mean is smaller, and hence the standard error is smaller. Okay, so replication allows that precision. Precision means lower variability. So we improve our precision or decrease the standard error of the mean by increasing replication. The topic we're starting today is analysis of variance. So it is referred to by an acronym here. We pick up the analysis of variance. That's ANOVA. Some will refer to it as just AOV. ANOVA is most common. ANOVA methods allow us to test for a difference among 2 or more population means. So the first off, it says, why isn't this called analysis of means instead of analysis of variance? And we'll get to that question. All right, but the idea then, what we had been doing before was, could we compare 2 population means, and we using independent samples or dependent samples? We've done that. All right, we talked about the 2 different types of t-tests. We talked about what if those were proportions. We've done that. Okay, now then we want to expand this. Suppose I have generically t different population means I wish to compare. So this lowercase t then is the number of levels of treatment in our notation. All it takes for that null hypothesis, all the equalities in between here, all it takes for this null hypothesis to be false is just one of them to be different. Okay, algebraically, we don't go in and change all those equal signs to not equal signs, because the notation is just super wrong. Okay, so you don't want to replace all the equal signs with not equal signs. That's not all it takes to make that false is just one of them to be different. Okay, the value of t here, it can be 2, or it can be something bigger. All right, the condition are assumptions. We have independent random samples from normal populations, and we have equal variance. So this is just a generalization of that 2-sample t-test that we did. Agreed? There we had populations 1 and 2 are normal, and we had sigma 1 squared was equal to sigma 2 squared. So we've extended that even further to all t populations. All right. Before we called this just an independent samples t-test when there were only 2 groups. More generally, if we have 2 or more groups, this is referred to as a completely randomized design. That just simply means that we have independent samples. So if someone says they ran a CRD or a completely randomized design, they had independent samples. There's no pairing or grouping of observations. Once we get into designs, all we're really talking about in this course is a CRD. We've talked about paired experiments, but when we talk about completely randomized design, you'll see several acronyms in statistical literature for different design types. All right, notation. We've already seen T. T is the number of levels of a treatment or a factor for the number of populations you wish to compare. Okay. Each of these different treatment levels has a sample size, and so N with subscript I is our sample size for treatment level I. All right. If we add up all the sample sizes from I equals 1 to T, and whenever you add up across an index, a dot replaces that index, so that just simply means that index has been summed over. And so that's the sum of all the sample sizes is our grand sample size for the experiment, or overall sample size. So the values here of I that we're seeing in here, I ranges from 1 to up through lowercase t. All right. I believe earlier I was writing in uppercase y's. For some reason I've switched to lowercase, but don't let that disturb you. Okay. Yij, typically whenever you look at an observed value, lowercase is more appropriate anyway. Yij is our observation on the experimental unit J within treatment level I. Okay. So here again, I ranges from 1 up to T. We have T treatment levels. J then is 1, 2, and goes up to whatever N sub I is. Yi dot, so I start speaking in Morse code once we start here, because you start hearing me talk about dots and bars and things. Yi dot, the dot is where the J index occurs, so that means the J index has been summed over. Okay, and so that means we're summing from J equals 1 to Ni of all the Yij's, so that's just the total of the observations we see in treatment level I. If we divide that total by the number of items in treatment level I, so we divide by N sub I, then we end up with Yi dot bar. And so that's analogous to our Y1 bar or Y2 bar that we saw earlier. Okay, so that's our treatment level I sample mean. Y dot dot is I've added across both indices. So this says then that for I equals 1, you add up all of the N1 observations. Then you go to I equals 2, you add up all the N2 observations, and then you compute a grand total of those. Y dot dot bar is the grand mean, so it would be the grand total divided by the grand sample size. And then for each of our I treatment levels, we can compute a sample variance S sub I squared. So no change in notation for that S sub I, other than it was just S1 squared and S2 squared before. So just to illustrate the notation, make sure everybody's comfortable with the notation. When we look at our sample 1 here, so here we're looking at sample 1, observation 1, or treatment 1. Here we go. Treatment 1, observation 2, treatment 1, observation 3. Okay, over here. We could keep going. Treatment 2, observation 1, and so forth. And we have treatment 3, observation 1, right? We can fill in the rest. N1, how many items do we have in this sample 1? We have 3. There are 4 observations in sample 2. There are 2 observations in sample 3. All right, Y1 dot bar just simply says add these things up. 5 plus 7 plus 6 is equal to 18. Y2 dot bar, add things up, 17, 21, 23. Y3 dot bar is equal to 4. If we take each of those totals and divide it by the respective sample size here, 18 over 3 or 6, 23 over 4, and it'd be 5.75, and 4 over 2 is 2. T, we had 3 populations we sampled. Our grand total would just be the addition of the 18, 23, and 4. 41, 45. Our grand sample size is the 3 plus 4 plus 2. Grand sample size is 9, and our grand mean is the 45 over 9, which is 5. Okay? Just a simple illustration to make sure we're all clear with the notation. We can measure what we call total variation or total sum of squares. Variation is different from variance. Variation is just the sum of these squared deviations. Variance is divided by degrees of freedom, is variation divided by degrees of freedom. Okay, so anytime you compute a sum of squares or a variation, it has degrees of freedom. Okay, when you divide by it, that's when you get a variance, when you divide by those degrees of freedom. So first, all I want to do is consider this total variation. So what is this? This says how much does each observation vary about the grand mean for the experiment. Agreed? I'm going to break this up into 2 parts. Okay? And it's going to take me a few steps to get there. So I'm going to keep my sum across both I and j. I'm keeping the yij, leave some space, and I'm keeping the y dot dot bar inside the square brackets here. What I'm going to change then is if I subtract yi dot bar and add it back, I've not changed the value of the expression any, have I? I subtract the mean, add the mean right back. So the net effect is 0. But I'm doing this so I can look at grouping things. I want to consider these 2 things together, and because this is addition, I can group these 2 together. All right, so I want to leave this together as one term, this together as one term, and then square that binomial expression. All right, so when I do that, the double sum, all right, that means I would have this first term squared, yij minus yi dot bar squared, then apply the summation, plus 2 times the double sum across I and j. Remember cross product here, so this first term times the last term. So I'd have yij minus yi dot bar multiplied by yi dot bar minus y dot dot bar. So remember first term squared, inside last terms in first the cross product term doubled. All right, and then I have plus the double sum, square the last term. Okay? All right, what happens here? So here, this term cannot be simplified. This term is equal to, well, we'll keep it exactly the same, the double sum across I and j of each individual score minus yi dot bar squared. Beyond this course, but it has to do with the fact that the mean is the algebraic center of the data, and that this term is not involved with the j index at all, and that it factors out. This middle term goes to 0. Okay. This last term, notice in the side here, neither one of these y bars depends on j. So whenever I say I equals 1 and I'm adding up from j equals 1 to n1, I'm just adding the same thing up little n1 times. And then when I equals 2, I'm adding the same thing up little n2 times. All right? So that simplifies. I can write this then as just the sum across I times the ni times yi dot bar minus y dot bar quantity squared. The n is not squared. All right, this piece here, capital SS means sum of squares. Sum of squares due to error within a treatment level. What we're measuring is how each observation varies about its treatment level mean. How much natural variability is there in group 1 added to the natural error variability that's in group 2, so forth, all the way up to group T. This is a sum of squares, and this sum of squares is due to variation among treatment means. Right? How much does each individual treatment level mean vary about the grand mean for the experiment? All right, so this text here can be referred to as sum of squares due to error. Error within. Skipping the 0 here, of course. This piece is our sum of squares due to treatment, or just SSTRT is the shorthand. All right, so all this was total sum of squares. And so that's what I'm going to start on the next page here. Bringing this information forward, we have total sum of squares, total SS. Some references will write SSTOT. At a glance, it looks too much like sum of squares treatment, so I tend to write total sum of squares. Total sum of squares equals sum of squares due to error plus the sum of squares due to treatment differences. And again, in terms of summation notation, this is the double sum across I and j of yij minus yi dot bar, quantity squared, plus the sum across I of sample size I times the quantity yi dot bar minus y dot bar, quantity squared. All right, so these pieces of information are just available on the previous page. I just brought them forward for the top of page 8. Okay. Our null hypothesis was that our T population means were equal to each other. All right, we've kind of moved away from that in those last couple of note sheets when we were talking about total sums of squares and the two pieces it breaks into. One of the things to notice, though, I guess, here about our total sums of squares, I can write that summation for that over here as well. Yij minus y dot dot bar quantity squared. Here I'm adding up things that are squared. These are things that are squared added up, also squared items added up. There's no way I can get a negative number. Agreed? Sums of squares are always positive or non-negative. We could have 0, I suppose. But sums of squares are positive. We're not going to get a negative number. All right? So that means then if these two things add up to this piece over here, then these two are positive. One must be bigger than the other, or they ought to be about the same size, right? Okay, suppose the null hypothesis is true. If the null hypothesis is true, then my t-sample means should be all very similar to each other. Agreed? Okay. So if the null hypothesis is true and all these means are similar to each other, what happens to this expression? All these yi dot bars are close together, and they're all going to be close to this y dot dot bar. So if the null hypothesis is true, this term is going to get smaller, right? If the null hypothesis is false, then one of these is going to get a little bit bigger, okay? If the null hypothesis is true, then is it going to be the case that all of our yi dot bars are exactly the same? Well, probably not. There's going to be some difference there, but it ought to be just similar to what we see due to random variation alone, rather than saying there's something going on with the populations, right? Okay, so if the null hypothesis is true, this is going to be small, and it's going to be another measure of error variation. This is always going to be a measure of error variation, experimental error. That's always measuring experimental error variation. Okay, but if there's no treatment differences, no differences among the mu's, this also measures error. And so that's what these three statements here say. Okay, so put the same formula forms at the top to point with. I didn't write. I should have typed them in after the first one, but we'll write them in here real quick. Okay, now consider what happens if the null hypothesis is false. If the null hypothesis is false, then at least one of the mu i's is different from the other. And then the yi dot bar that estimates that mu I that's different is going to tend to be different than the other y bars. Agreed? Okay, so if at least one yi dot bar differs from the others, what's going to happen to this term? It's going to tend to get bigger. Okay, so sums of squares gets larger as the larger that difference is, or the more different that y bar is, the larger SS treatment becomes. Okay, and so if it is false, then the sum of squares treatment is larger than what we'd expect due to random error alone. It means there must be something going on with the treatments, right? Among those different levels. Okay. This sum of squares error sum of squares error measures error variation or experimental error. That's this piece here. Sum of squares treatment measures variation among treatment level means. How different are the treatment level means from the overall mean for the experiment? Okay. As I said a few minutes ago, every sum of squares has a measure of degrees of freedom associated with it. Always. Okay. So when we break things up into pieces, our total sum of squares is equal to the sum of squares error plus the treatment sum of squares. The degrees of freedom are also additive for those sums of squares. Okay, our degrees of freedom here, we'll talk about our degrees of freedom total, our degrees of freedom for error, and degrees of freedom for treatment. Okay, so the degrees of freedom are additive also. Our total degrees of freedom is grand sample size minus 1. Our error degrees of freedom are grand sample size minus the number of populations being compared. And the degrees of freedom for treatment are equal to the number of populations being compared minus 1. So written this way, what I mean then is that degrees of freedom total is equal to this quantity is degrees of freedom error, this quantity is degrees of freedom treatment, rather than write out all three equations. Whenever you divide a sum of squares by its degrees of freedom, the result is a mean square. All right, so how these terms are read then is mean square treatment takes the sum of squares treatment, divide it by its degrees of freedom. You could write in the summation formulas if you wish. That's why the blanks are there. I kept it a little bit empty here on purpose. Okay. The mean square error is sum of squares error divided by its degrees of freedom. So it's usually just mean square, not a D, not in terms of squared. Pardon me. When we started, back on page 4, our conditions or assumption for analysis of variance. Okay. We were testing our hypothesis of simultaneous equality of the means versus the alternative. At least one is different. Our assumption here is of the equal variance assumption. What did we do in a two-sample case when we had the equal variance assumption? If we could make that assumption, the first thing we computed was the pooled variance estimate, right? Okay, same thing here. Okay, if the variances are equal to each other, then I need to compute a pooled variance estimate. That pooled variance estimate is mean square error. So in the case of where t equals 2, the mean square error in S sub p squared should be the same thing. Okay, so this is the short way to get to our mean squares. Because this is an introductory class, we see some hand calculations. All right, after this class, then we get a little more real world. Okay, we get there in this one too and start using software, but so that you understand. Okay, total sum of squares. This was the initial formula I gave you. Okay, computational formula. So computational formula just means if you're going to do these by hand, you might find this a little easier. Okay, computational formula says square each observation first, then add them up. Minus C, which some references call that a correction factor, and so that means it's correcting for the overall mean. So here the correction factor is the grand total squared divided by the grand sample size. Sum of squares treatment can be written as a function of C as well, although if you don't have very many treatment levels for values of t that are small, this top formula actually is not that bad. Okay, sum of squares error. Not all references emphasize this, but use this formula here. If you can compute the sample variance for each of the treatment levels, then doing this is a lot more efficient than going through all of these. So all of these squared deviations. Because total sum of squares is the sum of the error sum of squares and treatment sum of squares. If you know any two of them, you can get the third, right? Or if you can get these two, then finding sum of squares error is easy. So I think our authors tend to drift towards this, but this is actually probably a little more feasible than trying to get this one in my mind. So. All right, So that mean square error is just a generalization of the pooled variance we saw in the t equals 2 case. So mean square error is equal to the sum of squares error divided by grand sample size minus the number of populations being compared. So if we expand this out using the SI squared that we saw in that formula on the previous page, this would have N1 minus 1 times the quantity S1 squared plus N2 minus 1 times S2 squared, and we'd keep going until we get all the way out to the group T minus 1 sample size times S sub T squared. All this would be divided by N dot would be N1 plus N2 up through N sub T minus T. What happens if we have T equals 2? Then we would just have these first two terms here, right? N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared all over N1 plus N2 minus 2, which we hopefully recognize that is indeed the S sub P squared that we saw in the two independent samples case. So we're not doing anything any differently than we did in the two samples case. We're taking all the variability from all T groups and pooling it together and dividing by the degrees of freedom then. And so this mean square error is a pooled variance estimate because it is doing the same thing S sub P squared did. All right, the mean square error measures variance within treatment groups or that variation due to random error. And so very often references will call it mean square within instead of mean square error. Okay, and so this is that same illustration I started with, except I went up to only 3 groups. If we had T treatment groups and however many observations they have, okay, we're measuring variation or variance within a group, taking all this variability, and this variability, and pooling that information together. Natural error variability, variability within a treatment level. Okay, just some other expressions you may hear or read. Okay, mean square treatment measures variance among the treatment means. So for our T treatment means, we have our y1 dot bar, y2 dot bar, all the way over to our y sub t dot bar. All right, here we're measuring variability this way among the means. That's what mean square treatment does, is measures that variance. All right, if the null hypothesis is false, and at least one of our treatment levels is different, then we know the variance among treatment levels will be larger than the variance due to random error. Okay? How do we compare two variances? An F-test. All right? So if the null hypothesis is true, the mean square treatment is another measure of error variability. If the null hypothesis is true, the mean square treatment should be much like the mean square error. If the null hypothesis is false, mean square treatment is going to tend to be larger than mean square error. If the null hypothesis is false, then the variance among treatment means is going to be larger than the natural error variance. Okay, so I am looking at a test statistic. All right, and it is going to take the ratio of mean square treatment divided by mean square error. Mean square treatment will always be in the numerator. All right? If the null hypothesis is false, this ratio is going to tend to be large, and large only. All right? If F gets close to 0, that's not an indication of H not being false, is it? Okay, so it's a right-hand test only. So our rejection region is F greater than or equal to an F determined by right-hand area alpha. What are the numerator degrees of freedom? Well, how many degrees of freedom go into mean square treatment? T minus 1. Denominator degrees of freedom. How many degrees of freedom are there associated with the variance MSE? N dot minus T. Okay? Makes sense? All right, so whenever we compared two sample variances before, and our numerator degrees of freedom and denominator degrees of freedom were those sample size minus 1 measures, that was for that application. This is a different application for F. So this application has different variances. These variances have degrees of freedom that are determined differently. So we look at those degrees of freedom then to determine the degrees of freedom associated with this the critical value of F, and then also in determining the p-values. Okay, so now we have a lot of information here. We've got sums of squares, mean squares, we have an F statistic, we've got a lot of things going on. Okay, so we want to be able to arrange all of our calculations such that they can be uniformly presented. And to do that, we call the table an ANOVA table, or analysis of variance table. We have a column for source of variation. Later on, you'll just see me shorthand that as source. We have a degrees of freedom column, sums of squares, mean squares, and our overall F statistic. Okay, our treatment, if we know more specifically what the treatment label is, we would put that there. Our experimental error and total. Total doesn't have to be at the bottom. Some people put it at the top. I always put it at the bottom. Okay. Our treatment has T minus 1 degrees of freedom. Our experimental error has grand sample size minus T degrees of freedom. The addition of these two is N dot minus 1, which was also our definition, or what we define total degrees of freedom to be. All right. I'm not going to write the computational formulas here, but sums of squares, so then we would enter here the sum of squares due to treatment. Here would be the sum of squares due to error, and then the total sum of squares. Okay, our mean squares, then if you want to write sum of squares divided by T minus 1 here, or if you just want to put the mean square treatment and the mean square error. All right, and our value for F is in line with treatment. So F is equal to mean square treatment divided by the mean square error. Again, mean square treatment is always in the numerator. When we look at this on the mean squares, these mean squares are each sum of squares divided by its corresponding degrees of freedom, except for total. There is no such thing as a mean square total. Okay, and so here, this F test, this right-hand test for comparing variances, I'm using to test means, right? That's where analysis of variance comes from. Why is this a right-hand test only? Because doesn't this kind of have a two-sided interpretation? If it's false, you'd reject if either one of the mu i's is much larger or much smaller. Isn't that two-sided? It is. But why is this F test then right side only? Because we've taken all those differences and squared them. So all those differences that were both a negative and positive have been squared, so everything shifts to positive. Right? Okay, so here again we can write our rejection region. We reject the null hypothesis. if our value for f is larger than that determined by an f with right-hand area alpha, numerator degrees of freedom t minus 1, denominator degrees of freedom n dot minus t. Now then, if you keep going in the next course and some after, there are other ANOVA tables, and the degrees of freedom then can change. There are different expressions. Well, and in fact, we get to a different ANOVA table in this course a little bit later in the course. Okay, so all ANOVA tables are not always t minus 1 and n dot minus t degrees of freedom. For this application being the comparison of t population means using independent samples. For this application, these are the degrees of freedom expressions. Okay?